Okay, so some examples of how to use estimating and accuracy using significant figures and rounding to a given degree of accuracy. So significant figures, we've got to remember that if we've got a number like 31.62 and we want this to one significant figure, then we find the first non-zero digit and we start counting from there as significant. So the first non-zero digit in this example is the 3, and that's in the tens column, so it's telling us to round to the nearest 10. So in this case we'd say it's 30. It's either 30 or 40, and 31.62 is less than 35, so less than halfway to the next value up. So when we look at these then, we look for the first non-zero digit, decide what place value it is, and then round to that place value. So here we've got 1, it's in the tens column, so it's asking us to round to the nearest 10. So 19 is nearer to 20 than 10, so that will be 20. 0.85, our first significant figure, is in the tenths column, so we're asking ourselves, is it 0.8 or is it 0.9? And because it's halfway between, we round up, so it'll be 0.9. This time the first non-zero digit is in the tenths, hundredths, thousandths column, so we're asking ourselves, is it going to be 0.004 or is it going to be 0.005? And halfway between, well, the 4 would mean it would go to there, so it's going to be 0.004. Halfway there, if you remember guys, would be in 0.0045, and 4.8 is less than that. Here we've got the 2 is the first non-zero digit, it's in the 10,000s column, so we're asking ourselves, is the answer going to be 20,000 or is it going to be 30,000? Well, halfway between is 25,000, and 25,400 is greater than that, so it's nearer to 30,000, so we would say 30,000. The next question is asking us to approximate some calculations by rounding to one significant figure. Usually a good way of getting a quick feel for what an answer might be. So 18.8 is near to 20, 31.2 is near to 30, so there's one significant figure. So 2 times 3 is 6, and then we've got a 10 and a 10, so when we times by 10 and times by 10 again, it's like times it by 100, so it becomes 600. To one significant figure, 61.2 is 60, 5.92 is 6, and 60 divided by 6 is 10. 37.2 is close to 40 to one significant figure. 314, well, the 3's in the hundreds column, so it's going to be 300 to one significant figure. And 59.2 is going to be 60 to one significant figure. If we divide all of these by 10, that will give us a smaller calculation to do, but we'll do it in stages. So 4 times 3 is 12, times by 10 times by 100 is the same as times by 1000, and then we're dividing by 60. So divide both of these by 10, and then we've got 1200 divided by 6. Well, 12 divided by 6 is 2, and then we've got the 100 left over, so the answer is going to be 200. Here we've got in the hundreds column is the first non-zero digit, so it's nearer to 800 to one significant figure. 21.5 is close to 20 to one significant figure, and 9.6 is 10. So if we finish that, so we've got 20 times 10, which is 200. Divide both of these by 100, then we're left with 8 divided by 2, which is 4. So our estimate for that calculation would be, we'd expect to get an answer of 4. This question goes on to 4 significant figures, right, so we've got to use estimates to decide which one. So again, if we round to one significant figure, it usually gives us a quick way of getting a feel for what's going on. So 43,000 is 40,000 to one significant figure rather than 50,000. 56.3 we could say is 60, and 7.4 is going to be 7. So if we notice, the 60 times 7 is 420, When we rounded the top number here, 43,270, we rounded it to 40,000 to the nearest one significant figure, but because the denominator of this division now calculation is 420, we could actually write 42,000 because 43,270 is close to that. That allows us then to divide both of these by 10, and we've got 42 divided by 42, which is 1, and then we've got 100 left over. So we're expecting this answer to be around 100. So when we look at these calculations, we can see that this is the closest, so we're going to estimate that the answer should be about 100. So to four significant figures, we think the answer is going to be 103.6. We wouldn't have a calculator in the exam, but obviously we can just quickly check to make sure. So 56.3 times 7.42, close the bracket, equals. So to four significant figures, 103.6. Okay, so now we're coming on to accuracy of measurement. So we've got Lawrence's weight is 84 kilograms to the nearest kilogram. So that means there must have been a scale that was measuring in kilograms, because it's to the nearest kilogram. So 84, 83, 85 kilograms. They gave the measurement as 84, but that means there was some region where they decided that they was going to round to 84. So there's a thing called the lower bound and the upper bound, and basically these limits will allow us to answer this question, because the question wants the maximum weight and the minimum weight that it could have been, because it could be any number between the lower bound and the upper bound. So the lower bound would have been 83.5 kilograms, the upper bound would have been 84.5 kilograms, and what we need to remember is that the weight, just call it W or something, it can't be the 84.5, but it can be anything up to there. You'd never be able to measure the difference between 84.5 and 84.4999 recurring, but it is a boundary, so we put the less than sign. And we could have had any weight down to and including 83.5, and this is known as the error interval. So if you ever get asked to calculate an error interval, and they're asking you to find the lower bound and the upper bound and use the appropriate inequality signs to show what the measurement could have been between. So it said write down the maximum that Lawrence's weight could be. Well, that's the largest value, so the upper bound, so it could have been up to, but not including, 84.5 kilograms. Write down the minimum that it could have been. Well, that's the lower bound, so 83.5 kilograms. Remember units on measurements, guys. Okay, so question goes on. The time to pump water out of a filter cell is 12 minutes to the nearest minute. It says write down the shortest time. Well, that's crying out again that we're talking about error bounds here, error intervals. So we need to work out the lower bound and the upper bound. Because it's 12 minutes to the nearest minute, then again there was a measurement scale going on here that they decided not to give it as 11 minutes, they gave it as 12. So measuring in minutes, then the boundaries are the halfway. So 11.5 mins and 12.5 mins, less than, greater than or equal to. So write down the shortest time it could have been. Well, the lower bound was 11.5 minutes. The longest time it could have been is the upper bound, so 12.5 mins. What is the error interval? Well, the error interval is the time between the lower bound and the upper bound of the measurements. So it's less than 12.5 minutes, but greater than or equal to 11.5 minutes. So that's what the error interval is. So the time could have been anything between those two times. It then goes on and says express your answer to B as a percentage of an hour. We've got B as 12.5 minutes. When we want to write one number as a percentage of another, then we need to remember the usual way would be to do a fraction with the two numbers and then times by 100 to turn the fraction into a percentage. So this one is about write your answer to B, which was 12.5. Fraction of an hour, we'll need to remember that's 60 minutes in an hour. And and 12.5 is a calculator question. Divide by 60 equals times 100 equals. They've asked us to round the answer to the nearest whole number. So the answer on the calculator is 20.8. So to the nearest whole number it will be 21%. This question wanted a percentage. This question talks about a circle has a radius of 6.4 metres, rounded to one decimal place. Calculate the largest possible area. Well, the trigger word is area, in the sense that we need a formula. So we need to remember that the area of a circle is equal to pi times the radius squared. It wants the largest possible, so that's kind of shouting out at us that we need an upper bound, because it's talking about accuracy of measurement. We've rounded this to one decimal place. So this scale would have been 6.4, we're measuring to the nearest tenth, so the scale would have gone 6.3, 6.4, 6.5, so our boundaries would be halfway between. And the maximum, because we want the largest possible area, then the maximum radius would have been 6.45 metres. So when we want to calculate the area, then it's going to be pi times 6.45 squared. So put that in a calculator again. So pi times 6.45 squared, 130.7 to one decimal place. So 130.7. The question rounded things to one decimal place, so the answer should really be the same accuracy. You can't really create an accuracy that wasn't there. So 130.7 square metres. Okay, so that's some examples of rounding to significant figures and using accuracies of measurement to find lower bounds and upper bounds and error intervals. Hopefully you've used them, guys.